Alrighty, this is the first of several tutorial videos that are being created and designed to help you understand how to use the Tsunamis package to analyze your own historical tsunami. In this video, we'll give an introduction to the importance of historical tsunamis, and also an overview of Tsunamibayes, what it's doing, how it works. To kind of give some context as well to this collection of tutorials, this is designed to be an introductory user guide. We're going to walk through some concepts, the code that we've written, and the hope is to give you an idea, start to finish, of how you can analyze your own historical tsunami. This is meant to be an overview. I'll attach more resources, papers, and more detailed information. Here, we're just trying to get the essentials of what you need to know to be able to apply this for yourself. This is meant and geared towards new students or people that are coming to work with us in our research project here at Brigham Young University, but it's also meant to be a collaborative tool so that our colleagues and people over the United States, over the entire world, can use this program for their own benefit. So we'll get started here. In this video, we're going to talk about why do we need to analyze historical tsunamis. We'll take a look at what is Tsunamibayes and how does it help in this analysis. We'll talk about the resources that you'll need in order to analyze a tsunami. And then we'll look at what is kind of the end goal, the output that we're looking for in this program. So first of all, again, tsunamis play a big role in terms of natural disasters and the impact that they have, especially in the Pacific Rim. And the area of study that we focused on a lot with our program has been Indonesia. However, this can be applied to other faults around the world, of course. But in the examples I'll give, we'll focus here, mostly because Indonesia is such a tectonically active area. We have applied the Tsunamibayes code to several events in this region. And kind of looking again towards the importance of kind of historical tsunamis, we need to first answer, what is a historical tsunami? And quite briefly, it is a tsunami essentially that occurred before we had instruments that could take very accurate seismic data. Nowadays, whenever an earthquake occurs somewhere along a fault, we can pinpoint it very specifically to the epicenter. We can figure out what was its magnitude, what time did it begin, what did the shaking look like, etc. But we've only had that for about 50 to 70 years. And the difficulty of this is when we talk about two plates coming together in this fault interface here, it's a buildup of pressure. And again, obviously we know that the earthquake is essentially these plates slipping and that pressure releasing. But that occurs at different points along the fault at different periods of time. And this cycle of building up pressure and releasing can occur over hundreds and even thousands of years. So in order to be able to predict areas of the fault that are going to slip, that are going to cause earthquakes in the future, we need to have a more complete background of earthquakes and seismic events that have happened in the past. More specifically, we need to identify places known as seismic gaps. These are essentially places along the fault that we know are continuing to build up pressure and haven't had a seismic event relieve that pressure in the recent past. Again, our hope is to be able to get a better picture of where these seismic gaps are, so that we can predict where earthquakes will strike. In this example, this is a seismic gap that was present before the 2004 earthquake and tsunami that occurred in Sumatra that was so devastating. So our Tsunamibayes package is intended to allow you to be able to identify where historical tsunamis have occurred so that we can complete this picture. And this historical tsunami problem is a classic example of an inverse problem. Essentially, we know that the earthquake came from somewhere, a specific location with a certain magnitude, and it causes several effects. We can observe that. We can see what the outcome of that was. But the hard part is usually, especially when it comes to historical things, that we don't have this very precise pinpointed location of this earthquake. All we have are the observations, and we have to backtrack to figure out what was the source and the event and the associated parameters of that. Inverse problems are everywhere. But again, specifically in our context, we want to be able to take observations about the size of the wave, the time of the wave's arrival, the damage from the wave, the shaking, these things that we can kind of observe as the after effects and that these people observed on their respective islands, to be able to use that as well as our known laws of physics, to be able to backtrack that in order to pinpoint where was the epicenter of the earthquake most likely to be? What are the dimensions of that fault rupture that occurred? What was the magnitude of that earthquake? All these things, again, are helping us to pinpoint these seismic gaps that are there. And the great thing is that we have wonderful tools that allow us to be able to model, hey, if I have an earthquake occurring right here and it has a certain magnitude, what is that wave propagation going to look like? We have very good tools that can do this and approximate these wave distributions fairly well. Now the question becomes, hey, if we have these tools and if we have this collection of observations, how do we connect those? What methods and statistical strategies can we use to put those things together? So in order to do that, let's look at kind of what the Tsunamibayes program is doing itself. And here is essentially just a brief overview of kind of the inputs, the Tsunamibayes program, and the outputs that it provides here. Let's begin. I think it'd be best to begin with the actual Tsunamibayes program. Built into that, the Tsunamibayes accesses another Python package known as GeoClaw, and this is our tsunami simulator. It helps us to be able to measure kind of how a certain earthquake disruption causes a wave. How does that wave propagate? It also has a built-in capability to run thousands upon thousands of samples in something that we call MCMC chain. We'll get into more of that later. And it also has the ability to compute probabilities of these combination of earthquake parameters. Essentially, hey, if I have an earthquake that begins here with these characteristics, this magnitude, and I'm able to simulate that, what's the probability that that's the earthquake that did happen for this historical event that happened hundreds of years ago? And out of that, we eventually get our desired output, which is our best guess of what that earthquake looked like, the best guess of that source. Again, this is this inverse problem that we're looking at. In order to accomplish that, we need quite a few inputs. We need the actual historical accounts from various regions around this event of people that wrote things down in newspapers or whatever it might be. We need data about the actual fault plane, so the tectonic plates and their interface, the geometry of that, other characteristics. We need to have the bathymetry and topography data of that region. We can also input prior information from past earthquakes on that same fault into our program to be able to help constrain the guesses that we're making about what earthquake occurred. And then we can also add other geological constraints to kind of limit the sample space that we're using. Again, we will get much more detailed into these as we go along. But these different sections, these inputs, are going to be the subject of future videos, because a lot of this is kind of the things that need to be prepared. Because essentially, we need to take all these inputs and collect all this data. But we also need to translate it to a usable format for the program. We need to change qualitative information to quantitative information, and with that, account for the uncertainty that is with it, all that data there. So let's again just summarize kind of what will you need. So you're wanting to analyze the tsunami. Let's make sure that we have the essential pieces before we begin this very, very long process of getting everything prepped. First of all, you will need anecdotal accounts, essentially newspapers, historical documents of people, military leaders, etc., that jotted down observations of what the tsunami looked like. We'll get into much more of this later, and we'll also attach resources of catalogs and libraries and places that you can find that have records of these historical tsunamis that occurred hundreds of years ago. You'll also need bathymetry and topography data for this region. Again, we'll attach and talk about how do we get that, how do we compile that. Again, the bathymetry data is kind of the elevation and depth of the seafloor. Topography is now kind of like the coastline and the islands and the places that the wave is landing. What does the elevation and topography of that region look like? We'll also need access to a supercomputer, because we're running thousands and thousands of chains. It becomes very, very computationally difficult, and we need a lot of computing power to do that. And then we also need the GeoClaw ClawPack software package, which is a free package we'll walk through how do we get that, how do we access that, how do we use that. I just wanted to briefly show kind of this cool thing of what GeoClaw does. It has this power to be able to simulate, hey, when an earthquake happens and the seafloor breaks and has this sudden change, what does the wave propagation look like? And it's able to model that and follow that wave all the way to when it makes landfall somewhere. And it's able to help us measure the wave heights and the arrival time. Again, just all the characteristics we might need about how that wave is propagating. Here's another image of, this is an actual GeoClaw simulation here that someone visualized. And again, you can kind of see how it's able to begin kind of a wave and propagate that and measure how that wave is going to propagate with kind of the topography here above the water and then the bathymetry below. So very, very powerful, awesome tool that we have. We'll also need access to something called ArcGIS software. We'll talk about where you can find that, how you can get access to that. But I think an important thing is that you will need geology experts that you can consult with about this event. Because kind of as we talked about, you'll need to be able to constrain kind of the geological possibilities that are there. So we need to have people that understand earthquakes, tectonic movement, how that occurs. We need people that understand Python and how to run that, people that understand how to run the supercomputer. So you're going to have a collection of people, or at least access to people that have these capabilities and these skills. And then we'll also need the actual Tsunamis package that our research group at BYU has published on GitHub. And again, I'll attach a link of where you can find that as we walk through these things. So to kind of finish up this introductory video, let's talk about what is the output that I'm going to get from Tsunamis. I collect all this data, I input it, and I want to pinpoint where this earthquake came from. And this is a really awesome visualization of how Tsunamis is sampling thousands upon thousands of different combinations of earthquakes. And this is going to visualize kind of as it's searching in different possibilities for where it's going to be searching for the latitude, longitude, location of different earthquake possibilities and finding kind of what is the best probability, which one is most likely. So I'll watch that here. I'll speed it up a little bit as well. And you can see that just it's having these samples, which are represented by these lines here, are just jumping all along kind of this fault interface that kind of runs along this arc here. And you'll see that at first we're starting here, but eventually we converge to a much more central location. We're still jumping around because there is still uncertainty with that. We can't pinpoint the exact location, but we do converge into a fairly concentrated area. And at the end of this program running, we're able to have that collection of samples and look at where that is converging. We're able to see kind of as the software is running things statistically, what is the best guess we have for the location, other characteristics of the earthquake that occurred.